Knowledge Exchange Forum, today brought to you in collaboration with the Reformers Project for Renewable Energy Valleys, as well as the IEA's Heat Pumping Technology Collaboration Program on, IEA's Technology Collaboration Program on Heat Pumping Technologies. We'll hear from the Annex 61 later today. Earlier in these knowledge exchange forums, we've talked about the importance of energy storage and thermal energy storage in the grid. Today, we want to have a more specific look at how compact thermal energy storage in homes, the challenges that are being faced today. If we manage to solve those challenges, how will they be able to have an impact in positive energy districts in combination with heat pumps as well as energy valleys? So the agenda for today looks a little different. So we're going to start big, looking at the energy valleys and what it is, what this project is trying to resolve. We'll go to the home improvement. So what has person harm has tried harm has installed this in his home, but he has faced some challenge. So we'll hear about that and see how the thumbs up solutions can try to address those challenges. Then we'll talk about positive energy districts and open again to renewable energy valleys in the end of the conversation for the general discussion. So to get started, we will hear from Joep Sandik, from project manager at New Energy Coalition. Joep works as project manager, business developer, and account manager at New Energy Coalition, a continuously growing network of knowledge institutions. Sorry about that, of knowledge institutions, businesses, government bodies, and NGOs working together to accelerate the energy transition for a sustainable future. His core activities revolve around the development and realization and rollout of renewable energy valleys through reformers, positive energy districts, positive project in Europe, and circumventing the growing challenges of grid congestion faced by businesses and business parks in the province of North Holland. Having a background in science and innovation management, has a bachelor in science, and science and business and innovation, as is his master's, both with an emphasis on energy and sustainability. Joep is well equipped to bridge the gap between theoretical science and business operations to foster the implementation and commercialization of renewable energy innovations. Finally, Joep is a member of the Dutch Future Energy Leaders program initiated by the World Energy Council that provides platform for network for young and highly skilled individuals to discuss relevant energy issues in the Netherlands. So as you can see, we're very lucky and honored to have Joep here today. So thank you for joining us. So what can you tell us? What is an energy valley and what is this you're trying to achieve through the Reformers Project?
Yeah, thank you so much, Amelia. Thank you also for the kind introduction. Maybe do you want me to answer your question first or go to the slides? Because I think it's a bit self-explanatory. And then if the question remains, you can ask them afterwards.
Sounds good.
Will you be sharing your screen?
I can share my screen, absolutely. And you can just let me
Yeah,
know when
sure.
you'd
Thank
like
you.
me to change sides. Absolutely. There you go. Are you
Yeah.
seeing the right screen?
Yes, it's very clear. Thank you so much. And again, thank you for the opportunity to share a bit of insights about the Reformers project. Yeah, so it's I think similar to Funds Up, it's a European project. In this case, it's a Horizon Europe project. It's a project being funded with 20 million euros, so it's a rather large project. And we started on the 31st of October in 2023, and it's a 5-year project, so we'll continue until 2028. So we're now on our way for 15 months, and yeah, I will tell you a bit more about the project itself. So if you go to the next slide. Yeah, so the project is really about the development, realization, and rollout of renewable energy valleys. And that might begs the question, as Amelia already posed, what is a renewable energy valley? Because if you look into a dictionary, you won't find the concept of a renewable energy valley because it's a kind of a new theme in Europe. And the way that I at least often describe it, it's that it's energy positive. So in that regard, it has many similarities with positive energy districts. What is also unique, I believe, is that it integrates multiple energy carriers. So it's not only about electricity, but it also integrates heat, hydrogen, and for example, biomethane. And it also serves multiple end users. So it's not only focusing on the residential area, but also in this case on a business park and a rural area. And it also covers the entire chain of generation through storage, conversion, distribution to eventually end users. And within that valley, we want to optimize the energy flows as well. And if you see on the right picture, and by the way, I'm going very quickly, apologies for that, but I want to give the introduction and then give the floor to Harm, because then we can get a bit more into detail. But if you see, look at the picture on the right, you see 10 highlighted countries. So those are the countries in which we have consortium members. So in total, there are 27 consortium members within the project. It is coordinated by the University of Brussels, and we as New Energy Coalition are in charge or have the opportunity to coordinate the activities in the Netherlands and specifically in Alkmaar and Hilo, and I will get to that later. But you see the red dots, so that's the flagship valley of the project, and you also see 6 green dots, and these are so-called replication valleys. And if we then go to the next slide, I think we will see the flagship valley of the project. Oh no, first we see the renewable energy valley tracks. So the project revolves around 5 renewable energy valley tracks. The first one is about the generation of renewable energy, so both in electrons and molecules. The second one is about the storage, conversion, and distribution. The third one is about the monitoring and control. The inclusion of end users. The fourth one is about the monitoring and control, and the last one is about social, economic, and legal dimension to interlink that. And I think if you then go to the next slide, then you will see the flagship valley. Yeah, here it is. So this is the flagship valley of the project, and that is in Alkmaar and Hilo. So it covers 5 areas. In the center, you see the business park of Boeklemeer. On the top, the number 2, you see a residential area in Overdy. On the right, you see a rural area of Zuid-Schermer. And on the left side, you see parts of Hilo. And as I said, later on, we will go a bit more into specific use cases of Hilo when Harm will take the floor. That might ask the question, why is this the first flagship of is this going to be the first renewable energy valley of Europe? And if you then go to the next slide, there are a few characteristics which makes, I think, it quite promising. So there's already a lot of renewable energy over there. So there's solar, there are wind turbines, there's a bioenergy plant producing heat and electricity. There's already biomethane being produced, but it's also characterized by its existing natural gas assets. So there's a lot of infrastructure available that can actually be used also if you want to store or distribute other renewable molecules. And also within the flagship valley, we have Energy Innovation Park Alkmaar, which is a breeding ground for energy innovations. So there we can pilot and demonstrate certain technologies, especially focusing on green molecules. And one of the challenges that we have to overcome is the grid congestion issue, which is a very big issue in the Netherlands, and I think also becoming more and more an issue in other countries as well. So in that case, it might be sometimes better to not only electrify the entire energy system, but also use heat, but maybe a bit more on that during the later discussions of today. So on the next slide, you will see So this is the same picture as I showed you before, but here you see the plot of all the what we call energy innovations that we are going to demonstrate within the flagship valley. It's way too much to go into detail on right now, but it is good to mention that this project is really about demonstrating energy innovations. So I believe in thumbs up, it's a lot of focus on piloting, so maybe a little bit lower TRL. We are really focusing on TRL 6 till 8. So maybe some technologies or solutions within thumbs up can also be integrated later on in reformers. But here you see all of the energy innovations. I also try to highlighted the color. So you see some in blue that's focusing on the hydrogen value chain, some on green, which is focusing on biomethane. In electricity, the yellow one is more focused on electricity, and the red one is really focusing on heat. And I think, yeah, again, the specific case of the individual heat solutions in high-low will be introduced further by Harm. So I think on the second, or the next slide, I also wanted to try to display how all of the energy innovations fit together. And this is something that you might, if you're interested, can have a look at afterwards in your own time, because I think the slides will be shared. But I think this, at least with this graph or this the picture, we want to display how the different hubs within the valley are integrated with one another and what's happening and what time. And also in the annex of this slide deck, you will see how this evolves over the years. So currently there's not that much yet, but you'll see by the end of the year, a lot of energy assets will be deployed and developed further in the upcoming years. So I think that brings me to the next slide, which is focusing on the satellite valleys. Yeah, there we go. So as I said, this was currently really the focus. Harm and I are focusing on the flagship valley in Alkmaar and Hilo, but of course we also have satellite valleys, and these are focusing on the hopefully using the blueprint that we are developing within the flagship valley, so they can replicate the best practices in these 6 regions. Within the project, we're also developing a digital twin, and we're also using toolboxes that can support them in that quest to also become a renewable energy valley. And I think that was my presentation as quick as I could to hopefully give you a bit of a understanding about what the project is about. And if you want to know more, don't hesitate to reach out to me. I can tell a lot more about the project, but I think for now we can go a bit further into the details and specific case in relevance to the Thumbs Up project as well.
Thank you very much. And yes, we keep the presentations short so that we can have longer and more interactive discussions. So having said that, please, I would like to invite all of you to use the chat or the Q&A function to please write your questions so we can address them if you have any specific questions for you. But since we'll come back to the tie back around to the energy values, I think we can save other questions for the discussion towards the end. But I wanted to pick up 2 things that you're saying. I really like that you, why not connect other projects since you have this incredible test bed that you're testing and you're proving things. So my question to you is, thumbs up. Of course, we'll be in touch, and of course, hopefully, we'll be able to follow up on this. But other people, I mean, many people I see the guest list are involved in other projects. Would you be open to collaboration with them as well?
Yeah, I think the answer is definitely yes. Just in general, for these kind of projects, it's what easily happens, I believe, at least in my experience, is that you're really focusing on what you have to do within the project and really focusing on the reliance of the consortium members. But there are, of course, a lot of similar projects, or at least with some similarities, being funded by the EU or even by national or regional governance of governments. So yeah, I would say we can learn a lot from each other. I think our flagship valley is unique, but we can learn a lot from other flagships or other renewable energy valleys or other positive energy districts. So yeah, I would say just in general, there's a lot of opportunity to learn. And specifically, yeah, we met Emilia when we were in Milan. I was hearing about your presentation about the thumbs up. I heard about your aim within the project to develop thermal individual solutions. Well, we also need to implement that within reformers. So that's why I thought, yeah, let's link up and hopefully we can help each other out, so to say.
Thank you. And I will take that opportunity to link to Harms because when you said we have a challenge and then
Yeah.
the challenge is like, wait, that's exactly what we're trying to solve in Thumbs Up. So Harm, you are uh, here with us today. So thank you very much for taking the time since this is really just out of your own interests, since you have a journey and insights with you. his career began in 1970 in electrical engineering, and he later transitioned into the energy section and pursued a degree in business economics as well. So energy and business, again, it's almost like, is it a requirement to work at the Reformers Project to have both business and engineering as a background? One can wonder. His focus has shifted more towards consultancy in your own company, particularly in setting up production units, as a role you continued until 2014. That year marked a significant change as your family moved from Brainport City in Eindhoven to Halo, where you became involved in the Duurzame Halo Volunteer Foundation and subsequently the Reformers Project, which is a little bit what we're going to learn about today. You have been incredibly fascinated and re-engaged with the latest technological advancements through your comprehensive Reformers Project after so many years. You look forward to discuss these developments and sharing old day experiences with us today and learn from this. So I must say, we are also very excited to hear from you and hear your experience and your perspective, because one of the things that I find fascinating about these projects is really building the future. And if we collaborate and bring all our brains together, experiences, old experiences, new experiences, looking into the future, that's how really we're going to achieve the energy net zero economy for Europe by 2030 or 2050. Having said that, we're going to share, you have prepared a great presentation for us today, so let's hear
This project preceded the Reformers Project and was supposed to serve as a model for the PCM batteries included in the Reformers Project. However,
Sorry, Emilia, I think you muted yourself, and that's also when we didn't hear the sound anymore.
Still open.
Yeah.
You can hear it?
Yeah, we can hear it, but you shouldn't mute
you
yourself.
shouldn't
Maybe we
unmute
can't hear it
yourself.
anymore.
Okay, well, let's start again. Thank you for that. See, it's not, there's always has to be some sort of technical glitch. So hopefully this was the only one. Let's try again.
This project preceded the Reformers Project and was supposed to serve as a model for the PCM batteries included in the Reformers Project. However, during the panning phase of Reformers, problems arose which now make it difficult to apply this model. Due to circumstances, we were not able to perform the test properly, so the question of whether or not this is applicable is still open. It has not been calculated properly, and the correct control is still missing. To store all the energy in the summer and then use it in the winter requires a large heat storage, as at the top left of the sheet. People often think in terms of day and night, as in the picture on the right. You can turn on the washing machine when there is sun, but connecting a battery provides energy generated during the day can be used at night, as on the right-hand picture. But in winter, you need heat. Here's where PVT is used. This are solar cells with a heat exchanger in behind that extracts energy from the sun and the ambient temperature in the winter. These exchangers are outdoor units for the heat pump. Heat can also be stored and used later as input for the heat pump. If it gets colder in the future, you can use the stored heat for later and use it then as input for the heat pump. You can use the weather forecast as indicated in the graph below by looking at the differences of day and night temperature. These are the basic components with the aim of achieving as much self-sufficiency as possible for a private home. The core elements are the storage, essential for sustainable energy consisting of electricity and heat. This can be generated by PVT, where the PV part generates electricity and the temperature part feeds the heat pump, by means of some of the sun or simply the ambient temperature, where the panels then function as an outdoor unit. Then there is the heat pump itself, which must be fed as much as possible over time with the correct temperature in order to achieve a high yield, where the weather forecast and dynamic prices of electricity must also be taken into account. The entire system must be controlled. The challenge is to coordinate the elements in terms of capacity in the design for a good total system, and then to obtain a good algorithm for an integrated control. This sheet shows the total overview. This concept was chosen because there is no room for a ground source, and the connections of the old central heating system were in the attic, where the PVT can also be easily connected. The storage options are circled in red, as with the PCM tank right below. The green is the generating part with PVT divided in an electrical and heat part, right, a little above the PCM tank. Conversion takes place between direct current and possibly exchange of energy with the grid, depending also on dynamic energy price. But there's also conversion from electricity to heat, which is most efficient by heat pump if incoming temperature of the source is good. With PVT, this is critical in winter. This presentation will not include this electrical part, but should include it in the integral algorithm. The PCM and tap water tank are storage for heat, where this presentation is focused on the heat pump in relation to the heat part of the PVT and the PCM tank, indicated in the red dotted part in the sheet. We start when the heat pump can simply run based on the supplied temperature of the PVT panels. The PCM heat storage is full, and the PVT temperature is below T maximum allowed for the heat pump. There is, for example, a demand for tap water. The flow is indicated from the PVT with T big red arrow from the PVT right above to the mixing valve. The valve is closed from the PCM storage, so the flow is going straight to the heat pump. The flow with a lower temperature is going back to the PVT, as shown by the blue arrow. This is the normal course of events with a heat pump and is not further discussed here. PVT is an outdoor unit with the understanding that there is some extra radiation. Heat is brought in by those sun rays if there is sun, and also is more or less a heat buffer with all the liquid in the system. However, it is possible that the temperature of the PVT is too high for the heat pump that cannot go higher than about 25 degrees Celsius. In that case, the PVT is shut down or the flow is diminished, and the PCM storage is supplying additional. That storage should therefore not exceed the maximum temperature that the heat pump can handle. In that case, both PVT and PCM are above the limits of the required temperature, and the heat pump will shut down. In this case, the input of the PVT is more or less closed, and the red line from the PCM storage going to the heat pump, with the blue line back to the PCM tank, and partly the PVT. The set point of the mixing valve has to be set on the optimum temperature to the heat pump to get the best COP or efficiency of the heat pump. The PCM storage can be reloaded also later.
If the temperature of the PVT is high, when in daytime the temperature is high with sun on the panels and there is no heat demand, the PCM tank can be charged if the circulation pump of the heat pump can be controlled separately. Otherwise, an extra circulation pump is needed. By the control program, then T flows of the hot and relative cold flow form the PCM tank are mixed by the mixing valve. Then, the return temperature is higher than the temperature of the PCM and lower than TE PVT. This continues until the temperature of the PCM tank reaches the maximum allowable temperature for the heat pump, or until the temperature of the PVT is equal to or lower than that of the PCM tank. In case the temperature of the PVT is too low to directly charge the PCM storage, it is possible to do this using the heat pump. Suppose it is 11 degrees during the day, which is too low for charging the PCM tank, but in the night it is below 0 degrees. Then you can use the energy in the 11 degree in daytime by increasing it by the heat pump so that the storage can still charge B and can be used in the night when it's 0 degrees. This is then a kind of cascade system. The product, the heat at night, it is achieved in two phases. First, by filling the storage with favorable temperatures during the day, and second, use this intermediate product energy in the night. For the night, the control system is important to use an algorithm to ensure that the energy is distributed well to the demand in the evening and at night, depending on the weather forecast. It may not be efficient to use the PCM energy in the evening when the temperature is still 5 degrees, while it will only really freeze later. It is advisable to use the buffer when it is really needed to function efficiently. It should also be possible to charge the buffer if necessary, if the dynamic price of electricity is very low, via the additional electrical heating of the heat pump system. In that case, separate control of the CV circulation pump can be useful. The elements indicated in this presentation around the PVT and PCM must be integrated and controlled by a program that is yet to be developed. For this, the fixed variables of the components at the top left in the diagram around the heat pump, the PVT and the PCM, are required. On the right, the various measured values are given and the forecast for the weather and energy prices. In addition, there are other measured values from the heat pump, which are indicated at the bottom left. The output is the control at the bottom right of the valves, the circulation pump, and the heat pump, which itself also has a specific program with a heating line that also wants to optimize. This must be coordinated with each other and requires cooperation with the suppliers. As an organization with volunteers, this project was set up with a bit too much confidence in the competences and sometimes interest of suppliers. Components were delivered without proper coordination and good hydraulic and control systems. Initially, it seemed to work well and wasn't for the reformer's request, but later in winter performed to insufficient to use it more widely for the project. Knowledge of PCM, which in this case we were missing, but it has to fit in a total concept too. Our experience now is that each component supplier only looks at his own product, with no or too little knowledge for an integrated system. Mechanical engineering suppliers mainly try to use little to no electronic control, which is more difficult for them. In addition, small companies are not prepared to invest a lot of time in a project for a private individual if they are not guaranteed to make a larger turnover, a guarantee that we cannot give. Large companies are relatively too bureaucratic to take on these kinds of small projects. We are too small for tablecloth, too big for napkin. We are now looking for more knowledge about PCM and a good control algorithm. The current test system in the attic of a house can be mechanically adapted in line with this design. In short, this concept can only be made operational if it is theoretically better worked out as a whole, and if good control is possible. This again requires a somewhat better project approach, with more expertise that was not initially foreseen.
Great. Thank you for that recording. Very, very professional. I started getting in the chat. It was like, this is very impressive. So thank you, Harm. Are there any questions about this presentation already from the audience? Once again, please feel free to just raise your hand and open your microphone. That would be great. Or simply write them in the chat. While people think about this, I think I'm first a comment. It's really impressive and nice that you took your own time, your own interest to participate in these projects, unlike the rest of us who do it because it's our job. You really decided to go back. So what motivated you to do this and start testing and volunteering your own home to try these solutions?
I think energy is important. You see the fires, the waters, everything is going very bad. So do something useful with your time if you're retired. I think that's
and providing more insight. Next, let's go to, as remember, we're going back. So here we saw a challenge, and this is exactly the challenge that the Thumbs Up project is trying to solve. This is why we got the funding from the commission, and this is why we have 20 partners over 9 countries trying to come up with this. To present the Thumbs Up solution today, we have the honor of having Juan Carlos del Castillo. He's our technical coordinator for the project and works for CARTIF. Juan Carlos, you hold a Bachelor in Science in Industrial Technologies Engineering from the University of Valladolid and a Master in Science in Energy Generation Management and Efficient Use. From the same university, you have 6 years of experience working in a research and development company in the field of practice analysis with European projects at CARTIF Technology Center, where you're participating in national and European research and development projects focusing on district heating networks, energy modeling, and facility design and development. So Juan Carlos, would you like me to share the screen, or would you like to share your screen? Welcome, and thank you for joining us today.
Well, thank you for the introduction. If you want, I can share my screen with the presentation.
Sounds good.
So I guess you can see my screen, no? Okay, so well, I'm Juan Carlos del Castillo. I'm working in Fundación CARTIF, and today I'm gonna show you the ongoing work on the Thumbs Up project, and we will focus on optimizing the energy consumption with thermal energy storage. So, well, the Thumbs Up project is based on the development of 2 innovative thermal energy storage. With these storages solutions, our idea is to minimize the energy consumption from the grid and to reduce the peak demand mainly from the heat pumps. We will do this thanks to the energy surplus from the photovoltaic production. So the Thumbs Up project, we could say, is divided in 3 different phases. The first phase is the development of the 2 innovative thermal energy storages that are frackless and shortless. Frackless is based on PCM, phase change materials, and the idea of these storages working with daily cycles, while on the other hand we have the shortest that is based on thermochemical storage with cycles of around 4 weeks. So more or less with this we could storage daily, and also with our colleagues from Reformers were commenting, also during winter we could store the heat in a monthly cycle. Then the second phase is the validation and demonstration of these two technologies in 3 different applications: heating, cooling, and domestic hot water. And we will do this in first, we will validate this in industrial area with offices in Boecillo, in Boecillo, Spain, here in our, in one of our buildings. Then we will demonstrate these technologies in 3 different buildings: one single family building and 2 residentials, one without and with district heating network. And then in the third phase, we will replicate these technologies in 5 different places. So here, just a table with the summary of the main parameters of the 4 demo of the validation and the 3 demo buildings. So as I said, 3 are in Spain, the other one in Sweden. As you can see in the table, we are gonna work. We are gonna demonstrate these technologies with a high range of heat pump power and photovoltaic power, and also with and without the district heating network. So with this comparative approach, I think we can optimize the control strategy of these two technologies in different energy demand, energy networks, and in the 3 different applications, as I mentioned: heating, cooling, and domestic hot water. So, well, as you probably already know, I'm gonna show you just a simple explanation of how the frackless will work, the daily one. Here is the frackless. As I said, the sorters will work with cycles of 4 months or 4 weeks, sorry. But here, just a daily one. So as you can see here, we have first the heating demand, curve. Then a couple of hours later, we will start having the photovoltaic production from 8, 9, depends obviously the season and the country. And then with the pink line, we can see the heat pump demand. So the idea is to use the energy surplus of the photovoltaic production to charge our frackless and discharge this stored energy during the peak demand the following day, in case it's needed. There is where we are gonna explain later the control strategy and how it was developed. So just a simple view of the control strategy of the sorters and frackless. The sorters, due to there is a small heat pump inside, it has high power. So the strategy to charge will be charging during the night tariff. So we will minimize the cost of the energy, and we will discharge to reduce the electricity consumption from the grid. Well, I will explain later how we are gonna implement this in the thumbs up demo sites. And then the frackless, here it's more versatile, and the charging and discharging phases we could modify them, and we have more variety. So the idea is to charge the frackless with photovoltaic surplus always, in case that this power of the photovoltaic installation is higher than the power of the frackless, and to use this charged energy to discharge it and to reduce the electricity consumption from the grid. Here, depending on the application, we will use this stored energy in different time ranges. So, okay, in the moment that we understand how these two technologies work, the sorters can work. I mean, we have to think about the different applications if we want to apply it for heating, cooling, or domestic hot water. In the case of the sorters, we will use it for heating and cooling. And these sorters can work under any temperature conditions. But the frackless, okay, obviously we have to understand the application and to do some study, some analysis to understand the temperature range. We have to adapt this type of PCM to the temperature conditions. So in the moment that we analyze the optimal size of, the optimal capacity and the application and the temperature, we can analyze the discharge. As I said, the charging will be only in the case of energy surplus. The discharge, we will determine this thermal power. In the case, for example, if we are working with centralized frackless, we will analyze the power threshold of the heat pump. In the case that we are focusing on the distribution, like the air handling units or radiant or refreshing floor, we will analyze the thermal power demand of these applications. So, as I said at the beginning, the main goal of this is to minimize the electricity consumption from the grid and to improve or to increase the efficiency of the heat pump. Just here, I just wanted to show you as the first phase of thumbs up was already finished. For example, here I can show you the possible integration in the Cartif building, in the industrial one. So in the Cartif 3 building, the idea is to install the sorters for heating and cooling. We are going to install also a centralized frackless and a distributed frackless connected to the air handling unit. So as you can see here, for example, in the case of the sorters, that is the red line, we can see how we can charge it during different days and discharge it in different days, just trying to reduce the peak demand of the heat pump. What it means, we will reduce the electricity consumption of the building if we increase the efficiency of the heat pump. Then, for example, the blue line is the centralized frackless. In this case, the capacity is a bit higher, so it takes some depends on the season. In this case, it's in January. It takes some days because we need energy surplus from the photovoltaic production, as I said. So the yellow line means the energy surplus. So as you can see here, in the moment that we have some energy surplus higher than the power of the frackless, we could charge it and discharge it in the moment that we optimize the minimization of the energy consumption. The same with the distributed frackless. In this case, it's connected to the air handling unit. If we optimize it, we will see that, for example, in a month, we can have like 15, 20 cycles. in that case, it's because this capacity is lower than the centralized. So just to sum up, I just wanted to focus on the third phase, the replication campaign. We expect a really high impact of the thumbs up solutions due to we are working with really high energy densities. For example, in the case of Frackle's 65 kilowatt hour per square meter, while the shortest with 120 kilowatt hour per square meter. Then there is another advantage that the Frackless shortest, we are working with modular storages. So it will help to easily integrate this into buildings and obviously also into energy valleys or district heating networks. And well, with these thumbs up solutions, we expect to integrate these solutions in at least 1,000 buildings by 2030. With an investment of 200 million euros. This is everything. I don't know if you have any questions regarding the energy valleys or the thumbs up project in general.
Thank you very much, Juan Carlos. This is really interesting. So I actually have a question to Harm. What's your first impression of this solution, and do you think it will help you overcome the challenges you're seeing in your home? Or yeah.
Okay.
Yes.
In the first.
We are very honored as he is representing the International Energy Agency's, as I mentioned in the very beginning, heat pumping technology. Technology collaboration program on heat pumping technologies. It's a mouthful. I've tried. I've been working on it, and it's still a mouthful. So thank you for your patience. Professor Krishnan holds a master in science degree in mechanical engineering and industrial engineering at the RWTH Aachen University. He works as a professor for building system engineering at OST Eastern Switzerland University of Applied Science. He is an institute partner of the Institute of Energy Technology, IET, and deputy head of the study program on renewable energy and environmental technologies. His research focuses on heat pumps and system integration, as well as high-performance buildings and districts. In his professional life, he has carried out and chaired various development projects within industrial companies and research projects of the Swiss Federal Office of Energy, including the project management or operating agent of different annexes in the Technology Collaboration Program on Heat Pumping Technologies, the HPT-TCP, of the International Energy Agency. In this context, he also contributed to the implementation of the European Union Energy Performance of Buildings Directive, so EPBD, as we've heard much about, and in the frame of the EPBD Heat series. So Krishnan, thank you very, very much for taking the time to be here with us, and thank you for your patience. So I hope all these presentations have been interesting and relevant for you. But now, can you tell us a little bit more about, we looked at the thermal energy storage solutions, the PCM, but an important component are the heat pumps. Without the heat pumps, all this doesn't really fit together. It's much more difficult. So can you please tell us a little bit more about the heat pumps and the role they can play in positive energy districts?
Okay, thank you. So I'll try to share my screen. Thanks for the introduction. Do you see my screen?
Yes. It's not in presenter mode though.
Yeah, try to go to presenter mode. Yeah, now she should see it in full screen.
This is exactly how it should look. Thank you.
Okay, fine. So I'd like to present you the some interim results of the IEA HPT Annex 61. So give an outline of the project and then focus a bit on the thermal storage aspects. So we have 6 countries, 13 institutions, and we have 14 monitoring plants in the project. And yeah, of course, it's on positive energy districts. So basically heat pump integration into positive energy districts. Our scope is rather districts with 5 to 25 buildings. So from the monitoring projects, we have also consideration on groups of individual buildings, but also we have some monitoring projects which are really large installation. Still, the building number is limited, but there are up to 1,000 flats in some of the monitoring projects, so you can really call it a district. We focus on new build and on retrofit, and also we focus on residential and office buildings. So as in most of the projects, we have our task one as a state-of-the-art analysis, and you see the definition of positive energy district is still a bit vague or in progress, but there are three components you can focus on. This is the energy efficiency on the one hand, then the energy production options on the other hand, and then the energy flexibility to connect it to neighboring districts. We made an analysis of 50 districts in Germany and 50 districts in Switzerland, and also of the European projects in these 100 PEDs for 2025. And we saw that heat pumps is really a dominating technology side by side with cogeneration systems and with district heating. So heat pump have really a large share in all of these existing positive energy districts. Regarding the energy production, there are some legal boundaries still for PV installations. So it's a question where you can use the PV electricity, if you can transfer it to other buildings. And there are some legal boundaries yet, but they may be overcome in future. For instance, in Switzerland, it should be possible in future to distribute the produced PV electricity also among the building boundary or even the group boundary of the building installation. So you can form quite of local energy communities and share the PV produced on certain number of buildings. We also derived some boundary conditions for the system analysis, and we considered mainly an urban environment. So the main source of energy production would probably PV and not wind installation or biogas plants. So we are really stick to PV and in a dense urban environment. And I mentioned already the cross-country comparison. So we focus on the heat pump and the heat pump integration into the district. And so we consider different options for the integration, from the individual building integration up to the district integration. And we define some top level categories. We are currently figuring out what are favorable application fields of this heat pump integration. And we also derived some archetype PEDs to get a feeling how ambitious it is to really reach a PED in an urban environment where you don't have too much space around the buildings for additional energy generation. And of course, we did some technology evaluation and descriptions of these generic system solutions and the integration options. This is backed up by techno-economic analysis of detailed simulation work. So we have a lot of monitoring plans also for case studies. And linked to these monitoring plans, we also have modeling and simulation of the plans. So this is a bit exchange. So you have the measuring data from the monitoring plan, which can serve to validate the models. And then you have the models to do some optimization for the case studies and the monitoring. And afterwards, it will be derived the results to also be integrated for generic system solutions. So if you look at the generic systems, then of course, a common integration is a decentralized integration on the individual building levels. But if you go for the district level, then you also can think about just a purely electric connection of the buildings. This could serve to optimize the self-consumption of the buildings and in the district, to have some load balancing in the district and to share a common control. And if you have these local energy communities, you can also transcend the building boundary and transfer it to other buildings for the generated electricity. The next integration would be to have an integration on the source side of the heat pump. So you can have a collective source. This could be a central source, but this could also be a distributed source, which is connected by a source grid. So you have different contributions of favorable production sources and share it among in the district on the source side of the heat pump. Then you would probably have individual heat pumps still in the building and not centralized heat pumps, but you can also think about combinations. Then we have a so-called semi-centralized solution. This is a combination of a central system, so a centralized heat pump, which is connected to the buildings by a grid. This could also be replaced by district heating, something. And then you have a decentralized heat pump for dedicated application. For instance, the DHW operation is done by a decentralized heat pump, and the space heating operation is done by a centralized system. So this is a typical solution would be the booster heat pump, which just lifts the temperature level of the space heating level, floor heating of 35 degrees, for instance, and then produce decentralized the DHW, taking the source from this central grid. And then you have the fully centralized integration where you provide all the energy services for the buildings or for the cluster and district from a central source. So maybe separated for heating and cooling as well. And have just an installation of a heat exchanger and the storage maybe in the building. So these are our top level categories, and we are currently deriving favorable applications for that and describing the technologies behind these different solutions. So we have an increasing integration of the heat pump in the district. And linked to that, we have the monitoring plans, which also span from the individual building integration solutions to the centralized integration solutions. And we derive by simulation and monitoring also hints for the system integration of the heat. I mentioned these archetypes, and these archetypes were set up just to have a kind of, to figure out in an urban environment what are the potentials of the PET concept, and also to evaluate if there are gaps, if you can reach the PET, or if it's certain environments, a very ambitious concept, which is probably hard to realize. So we defined different building types for that. So we have single family building, a small and a larger multifamily buildings. You see the outline of the building types. And then you have also the office and the hotel for a non-residential application of that. This is also linked to a paper which is published, so I will give the DOI afterwards. You can go more into detail for the paper. So then this is the space heating needs in kilowatt hours per square meter and year of the different building types. And we considered new buildings, but we considered also retrofitting of existing buildings, and we have different levels of the retrofitting. So best retrofitting would be really a deep retrofitting, and deep would be in between the business as usual scenario where you have the existing building and the best retrofitting where you also have integration, for instance, of a mechanical ventilation heat recovery. And then we have the new building sector with and without, or the new building types with and without mechanical ventilation heat recovery. So we combined that to a certain archetype PETs, and then you have first, just a combination of single family houses, of new build standards. This would be the easiest to reach the positive energy district balance. Then you have single family houses renovated. Then the third type is a mixed residential application. You see this is single family houses combined with smaller and larger multifamily houses. And you see also displayed in the table the system technology which is installed. We divide or distinguish between an air water heat pump and a ground water heat pump. And then you have PV installation on the roof or even in the facade. So for the smaller buildings, it's mainly the roof. And for the larger buildings, it's roof and facade PV installation. Then we have a purely multifamily house renovated archetype. Then we have a mixed use new. You see it's a combination of single family and larger multifamily buildings. And then we have also mixed renovated use where you have also a share of office buildings. So these are the different archetypes. And if we look at the load curves, which are derived, so this is derived by simplified modeling just to get an idea if it's possible to reach the positive energy balance or not. And you see that the surplus is mainly sufficient to reach the positive energy district level for the first three categories. So single family houses, either new build or deep renovated. and the smaller multifamily buildings. But you see for the larger installations, if you look at the balance on the building footprint, then it will be very ambitious to get these positive energy balance. This is distinguished without and with battery, and you see that the battery can shift some surplus of the PV to the nighttime hours. So in the transitional period, you got a balanced load, but still in the winter, you have a lack of electricity generated by PV, and in summer, of course, you have the surplus. So it's considered as an annual balance, but still for the positive energy districts, the winter energy gap or the winter power gaps, that means a load mismatch between the production, which has a surplus in summer, and the consumption, which has a surplus in winter, is an issue, of course, for these districts. And here in the graph, you see different methods or different measures to overcome this winter energy and power gap, or at least to mitigate it. Maybe it's not possible to fully overcome it, as you see, but to mitigate it at least. And what is depicted here, you see on the y-axis, this is a reduction of the peak load to a reference, and the reference is the archetype 4 of this PET in business as usual building quality with a direct electric heating for space heating and DHW and without PV generation. So you have a poor reference, let's say, and then you can on the y-axis see the reduction of different measures of the peak load in wintertime, and on the x-axis you see the energy reduction from the grid consumption in an annual balance. And then you have different measures which are depicted. And you see if you increase your PV, then you can overcome basically the energy which is taken from the grid compared to the reference, so the relative reduction of the energy of the grid. And of course, with battery, you can further increase it, but you see that the peak load is not much reduced. So that is why the PV will not deliver too much energy in wintertime. So this energy will be used, but you cannot really reduce your load peaks or just moderately reduce your load peaks. If you look at the building envelope, then if you renovate the envelope to deep or even to best renovation level, then you see this is an impact both on the electricity from the grid, so the energy you take, but also there is an effect on the peak load reduction. So if you go to higher values, then you have a higher reduction of the peak load and you have a lower grid consumption of the electricity. If you look at further efficiency measure compared to direct electric heating, the air-to-water heat pump and the ground-to-water heat pump, you see that you can notably reduce your peak load. But on the energy side, it's not too much difference between the air-to-water heat pump and the ground-to-water heat pump. This is basically to auxiliary consumption in case of the groundwater heat pump. And if you have a higher DHW share in a well-insulated building, then of course the air-to-water heat pump is also good performance. So in this case, there's not too much difference for the energy consumption of these two variants, but of course the ground heat pump can reduce the winter peak, since in winter you have a better performance of the groundwater heat pump. And then you see if you have a large PV installation also with direct electric heating, you can reduce your energy and can reduce your peak load. And the global optimum would be a very well retrofitted building with a ground coupled heat pump, a large PV installation and battery. So what you expect if you combine the different measures together. So there is a link to this paper. So if you want to go more into detail of these archetype simulations and of the effects on the peak load and the grid electricity, then you can go for the paper where everything is outlined in detail. Since we have thermal storage, or first as a conclusion, that the PET on the building footprint can be very ambitious and is only can be realized for new or deeply renovated single-family or smaller multifamily buildings, then the PET concepts nevertheless make sense for a deeper understanding of technologies which move the building cluster or the district towards the PET. And also for PEDs, the load mismatch is an issue of summer production in the winter gap. This relates to storage integration as well. But as you've seen in the variants, it is really crucial for sustainable and resilient energy systems that you have a good building insulation and a good building efficiency. Load management and storage can be additional measures which increase the efficiency, and you have integral planning should be take into account the building and the system technology as a prerequisite to really reach a high efficiency and positive balance level. And the knowledge of the load curves, which have been developed here, can support the early design phase. And then I have another project which is not directly linked to the Annex, but which refers to these thermal storage, which is the topic here. And this is a system to retrofit the heating buffer storage with injection of macro-encapsulated PCM elements. Here we had a phase change temperature of 45 degrees, and this can increase the installed storage capacity. And the objective is to increase the PV self-consumption by this transfer of power to heat and store it in the heating buffer storage, increase the seasonal performance factor of the heat pump, because if you do an overloading just by sensible heat, then of course you raise the temperature more, and the heat pump has worse operating conditions. And if you can limit it, for instance, at the 45 degrees, then the heat pump works at a better efficiency. And also, if you store more heat, you can shift the heat pump operation more to daytime, where you have more favorable outdoor air temperature. In this case, it's an outdoor air heat pump which is installed. We have also installed this in a monitoring plant and measured 3 heating periods of it to gather experience with this behavior of the PCM. And the first heating period served as reference period. It was a purely water storage for the heating buffer. And the second and the third heat pump was equipped with different PCM elements, and we had some results on the operation of the PCM. Just a short outline.
I'm sorry to interrupt. All of this, there will be links in case people want to read more, right?
Yes.
Great, because we're running a little bit out of time, so if we can.
Okay, yeah, so I'll stop here. You will get the slides. Okay, yeah, thanks.
You can finish, but just quickly.
Yes. Okay. No.
I didn't mean to interrupt, just trying to make it so we have time for questions and answers in the discussion.
Yes, of course. Should be some discussions.
But really interesting. Are there any questions for Karsten as it is in the presentation?